Hello everybody, and welcome to our fourth video lecture. Today we're diving into the topic of representation theory. Hopefully by this point in your mathematical career, you can think of one or two reasons why representation theory might be important. Maybe you're motivated by its connections with harmonic analysis. Maybe you're into number theory or the Langlands program. Or maybe you've been running through some cool ideas in mathematical physics. In any event, you can find representation theory both in influence and application in a lot of different areas of mathematics. The starting point for representation theory, both historically and in terms of mathematical learning, is the representation theory of finite groups. Let's start out with a field and a finite group G. And a representation of G over a K vector space V is simply a group homomorphism from G into the automorphism group of V over K. Because the representation depends both on the automorphism and the K vector space V itself, we'll sometimes denote the representation as an ordered tuple pi V rather than just pi or V. An important alternative point of view is that we can think about representations of G as Kg modules. Here Kg is the group ring, which is the set of all formal linear combinations of elements of the group G with coefficients in K. The associated multiplication operation is done in the obvious way. With this in mind, there's a natural correspondence between representations of G and Kg modules, which is 1 to 1. In particular, this takes a representation pi over a K vector space V and sends it to the Kg module, also represented as V, where the module action is given by the sort of obvious action that we would expect. One of the most important representations of G is the regular representation. This is determined by Kg viewed as a module over itself. In particular, it's a representation pi of G over the vector space V given by Kg, wherein pi of G is the linear transformation from V to V, which acts on basis elements by group multiplication. In particular, it sends the basis element h of V to GH. The regular representation is important because we can find every other finite-dimensional irreducible representation as a direct sum end of V. In particular, the regular representation, Kg, decomposes as a Kg module into a direct sum of irreducible Kg submodules, with each possible isomorphism class of irreducible Kg submodule occurring at least one time. The multiplicities of each occurrence are determined by character theory. So this, at least, is the very beginning of representation theory for finite groups, and we'd like to find an appropriate analog in the setting of affine group schemes. To start out, let's let K be an arbitrary ring, so it no longer necessarily needs to be a field, and let's let V be a K module. Then I can define a functor, which I'll call V twiddle, from the category of K algebras to the category of sets. This takes a K algebra R to the associated extension of scalars of V. With this in mind, we define a representation of an affine group scheme over K. We just define this to be a natural transformation from G to the automorphism group of V twiddle, satisfying the property that pi r, which is a map from GR to the automorphism group of V twiddle R, is a group homomorphism. We denote the natural transformation as the order tuple, we denote the representation as the order tuple pi v, and we say that pi v is a representation of G on V. It's called finite dimensional if the K module of V is finite dimensional, by which we mean finitely generated, and it's called faithful if pi sub r is injective for every r. Let's think of an example. For sake of this example, K will be a field with characteristic 0. And I want to think about representations of the additive group GA. It turns out there's a very nice map from the set of nilpotent endomorphisms of a finite dimensional K vector space to the set of representations on that vector space. In a very real sense, this is defined by the exponential map. It takes a nilpotent endomorphism rho and sends it to the representation pi, where here pi must be some natural transformation from the additive group GA into the automorphisms of V twiddle. So for any particular r, pi sub r has to be a group homomorphism between r and the r automorphisms of V tensored over K with r. We do this by defining pi sub big R of little r to be the map from V tensor R to V tensor R, which acts on simple tensors by sending V tensor C the sum over all n greater than or equal to 0 of rho to the n V tensored with r to the n C. And one can check that this is actually going to be a homomorphism of groups. I apologize, there's a bit of a typo here. I need to divide this by n factorial in order to make the homomorphism work out. You can see the nature of the exponential function reflected in the definition. Moreover, because rho is nilpotent, we're not going to add up infinitely many terms, so we don't have to worry about convergence of this sum. This is really good, because without any topology in our field, we don't even know what convergence means here. It's interesting to note that this correspondence actually determines all the representations of G over V which are finite dimensional. I guess I don't need to say finite dimensional there because V is already a finite dimensional K vector space. As we mentioned before, the regular representation of G, in the case that G is a finite group, was particularly important. We'd like to come up with an analogous representation to play the role of the regular representation for affine group schemes. The left regular representation of G is defined by considering the coordinate ring of G as a K module. In this case, V twiddle takes a ring or a K algebra R to OG tensored over K with R. Now if I remember extension of scalars, this is exactly the same thing as the coordinate ring of the extension of scalars of G by R, where here, just as a refresher, we remember that the extension of scalars of G by R is the functor from R algebras to sets, which takes an R algebra R prime and sends it to G of R prime, forgetting that R prime is an R algebra and just remembering its K algebra structure. Now given a K algebra R and an element G in G of R, left multiplication by G defines a natural transformation from the extension of G by R to the extension of G by R. By unita, this corresponds to an R algebra homomorphism, and in particular an R module homomorphism, from V twiddle R to V twiddle R. Let's call this latter map pi R of G. In this case, pi R then defines a group homomorphism. Alright, there's a bit of a typo here. from GR to the automorphisms over R of V twiddle R, which is, as we know, OG tensored over K with R, or the coordinate ring of G extended to R. Furthermore, nothing's more natural than unita, so pi is going to define a natural transformation from G into aught of V twiddle. So this is a representation of G over V. Indeed, this is what we define to be the regular representation of G. Now let's also remember that our representation of a finite group G had an alternative description as a KG module, that is a module over the associated group ring. Also, let's remember that the theory of affine groups can be viewed as an extension of the theory of finite groups. In this extension, the group ring over here, KG, corresponds to the coordinate ring, OG. But we have to be very careful here. KG is in general a non-commutative ring, but it can be given a second structure where we view it as the set of maps, just set valued maps with no additional structure from G to K. This gives KG a bialgebra structure, making it a Hopf algebra. Similarly, we know that OG has a Hopf algebra structure. So this correspondence is such that the appropriate Hopf algebra structure, the one which is already commutative always, is going to be sent to the same sort of algebra structure on the right-hand side. So the typical algebra structure we think about for KG is actually the co-algebra structure under this correspondence. Now, as we said before, I can view any representation of G as just a KG module. In this same way, I would expect any representation of our affine group scheme G should have some sort of alternative description as a co-module of OG. To summarize, the one-to-one correspondence between representations of G and modules of KG in the finite group case should translate somehow to a one-to-one correspondence between representations of G and co-modules of OG in the affine group scheme case. This motivates at least the discussion of co-modules. To start out, let's just consider a K-algebra A. The multiplication operation on A induces a map of K-algebras, M, going from the tensor product of A over K to A. The identity on A corresponds to a map E from the field K into the K-algebra A. Then if I have any K-module V, specifying an A-module structure on V is the same as specifying a K-linear map from A tensor V to V, making the associated diagrams that you would expect commute. In particular, commutativity of this first diagram ensures that the action of A on V is associative, and commutativity of the second diagram ensures that the action of the identity element on V is just the identity. A comodule structure will be exactly the same thing, but defined for a coalgebra with all of the arrows reversed. To start out, let's consider a coalgebra, a K coalgebra C, with co-multiplication given by delta and co-identity given by epsilon. And let's not assume that the coalgebra structure here is commutative. A right C comodule is a vector space V over K with a K-linear map from V to the tensor product of V with C, making the following two diagrams commute. The first diagram ensures that the coaction is co-associative, and the second diagram is the analogous result that the identity element acts as the identity. Every bialgebra, in particular, is a coalgebra, and we just define a comodule over a bialgebra as just to be a comodule over the associated coalgebra for getting the bialgebra structure. And an important result is that this one-to-one correspondence between representations of finite groups and modules over the associated group ring KG carries over into the affine group scheme case. In particular, we have the following proposition. If I start out with an affine group scheme over a ring K and I let V be a K module, then there's a natural bijective correspondence between the representations of G on V and all the different OG comodule structures we can impose on V. This correspondence sends a representation, pi, to the composition of the map including V into V tensor A, and then the map from V tensor A to V tensor A induced from pi sub A of the identity of A, where here A is just the coordinate ring of G, and without loss of generality, we're taking G to be H superscript A. That is to say, the functor which takes a K-algebra R and sends it to the collection of K-algebra homomorphisms from A to R. In particular, then, the identity on A is an element of G of A. Proving this proposition has a lot of moving parts. For example, we need to show that this composition here actually defines a coalgebra structure. Moreover, we need to show that this map here is one-to-one. To prove the latter, it's actually more helpful to once again determine a map going in the opposite direction, which is to say, if we start out with a coalgebra structure rho on V, we want to send it to a certain representation of G on V. The particular representation that we send it to is the one which satisfies that pi sub R of G is the map sending V tensor R to V tensor R in such a way that the associated diagram below commutes. By showing that these defines a representation and that these two operations are inverses of one another, we'll prove that the correspondence that we establish is bijective. To start out, it actually is easier to just show that there's a bijective correspondence between natural transformations from G to the automorphism group of V twiddle to the set of k-linear maps from V to V tensored over K with A. This is one-to-one, and here I'm taking G again to be H superscript A. Let's start out with a natural transformation, pi, going from G into the automorphism group of V twiddle. Then for any G and GR, consider the diagram whose horizontal rows are maps from V tensor A to V tensor R, and whose vertical rows are induced by the representation. Vertical columns maps are induced by the representation. I actually need to fix a typo here, because in order for this correspondence to work, I need to replace the automorphism group of V twiddle with the endomorphism set. This won't be a problem later on, when we force things to respect the group structure, because then the image of G will have to be inside of the automorphism group of V twiddle. The naturality of pi implies that the square commutes. The induced map from V to V tensored with A over K, defined such that the corresponding triangle commutes, is automatically going to be K-linear. Let's call that map rho. The observation I want to make is that the value of rho also determines the value of pi rg. Specifically, once we know rho, we know pi sub a of the identity of A, because it's the unique extension of rho to V tensored with A. Once we know pi sub a of the identity of A, pi sub r of g is the unique map on the right-hand side, making the associated square commute. In other words, given pi, we define rho to be the restriction of pi sub a evaluated at the identity A restricted to V. And given rho, we define pi r of g on simple tensors by setting pi r of g of V tensor C equal to the value of the identity tensor G evaluated at C times rho of V. This establishes the one-to-one correspondence. What's left is to show that pi is a representation of G if and only if rho defines a comodule structure on V. To start out, the condition that pi sub k of the identity element of G of k, which I'm denoting here as 1 sub G of k, for that to be equal to the identity on V tensor k, which is just V, is equivalent to saying that the following diagram commutes. Here, this is the diagram that we were thinking about before for our bijective correspondence, but I've replaced G specifically with the identity element in G of k, and I've replaced pi sub r of g with the identity map on V tensor k. The top line here is simply the map that sends V to V tensor 1. So the commutativity of this diagram is exactly the same thing as the commutativity of this triangle. We'll remember that this was the second commutative diagram in the definition of a comodule. Next, for pi to be a representation, we have to have that pi rg times pi rh is pi rgh for all gh in G of R. Remember that the group multiplication map on G of R is induced by the co-multiplication map on A. In particular, the product of G and H is exactly the composition of the three corresponding maps. Then, using our commutative diagram, we can see that pi sub r of gh acts on a simple tensor, V tensor C, in the following way. Furthermore, the composition of pi r of g with pi r of h acts on a simple tensor, V tensor C, in the following way. This requires a little bit of simplification as we go throughout. The first equality is very simple. The second equality requires us to check one or two things. And then the third equality follows very easily from the second. In particular, pi rg times pi rh is equal to pi rgh if and only if the following identity holds for all v and v. Here I've taken c in the previous equations to be 1, since the linear extension that we describe is uniquely determined by phi in the first place. Excuse me, not phi, rho. I can rewrite the right-hand side as a composition of three morphisms. Then if we eliminate the last morphism, we end up with the condition that rho tensor R composed with rho has to be the same thing as the identity composed with the co-multiplication map, or tensor with the co-multiplication map composed with rho. In other words, we require that the following diagram commutes. And here I have a typo in the above. This R was just supposed to be the identity map. But this is exactly the co-associativity condition for the comodule action. So this proves that the bijective correspondence above restricts to a bijective correspondence between representations and comodule structures. This completes the proof. So to summarize today, we introduced the notion of a representation for affine group schemes. We also introduced the regular representation, and we showed that there's a natural correspondence between representations and comodules of the corresponding Hopf algebra. This correspondence is parallel to the typical correspondence between representations of a finite group and the group ring. But this is a pretty good stopping point for the day. I'll see you guys next time.